Welcome to my presentation. The topic is authentication technique based on image recognition, example of quantitative evaluation by probabilistic model checker. My name is Bojan Nokovic. I work at McMaster University as a sessional instructor and at Royal Bank Canada as a tech lead at API security squad. So in today's world, almost 50% of traffic at internet is generated by web robots or bots. And some of that traffic is good traffic generated by so-called good bots. They were used for website health check, to collect data for search engines, to verify some functionality of websites and so on. But most of the traffic, bad traffic, is generated by so-called bad bots that present false identities to bypass security, and they are called impersonators. So the goal of this study is to try to quantify the impact of impersonators on innovative and Royal Bank patented image-based authentication process, so that business people will be able to decide if this is going to be implemented and we need some improvements and so on. So there are two ways to quantify properties, either to build a system and then by testing and measuring, or to try to build some model. So we try to have a model approach. We had one presentation today when Papyrus is used for modeling, very nice presentation. So we are actually following similar path, but we are modeling now a probabilistic system that actually actions or transitions are taken with some probability to particular states. So in simple words, we would like to analyze how likely is that a bad bot or web robot will bypass security. Just a few words before we start looking at that about model checkers in general. Software model checking is known technique around for a long time. Traditionally, it is used like finite state machine model that is actually run to verify some specified property. Property is specified in linear temporal logic from the time of end of 70s, 80s. We see progress in this field. Recently, there was a lot of interest in probabilistic model checking. In this case, model of the system is built as Markov chains or Markov decision process that includes non-deterministic transition. Also, we can build model based on probabilistic time automata and so on. And the property is specified by a probabilistic computational tree logic formula. The goal is to determine if model that starts in some particular state S satisfies specified property. Today we have different type of model checkers. Probably the most known is TLA Plus, developed by Leslie Lamport a long time ago, and it's improving over time. Some are more focused on real-time system, like APAL. Some is more focused on concurrent or distributed system. We use PRISM, probabilistic model checker, that is initially developed by University of Birmingham and continue developing at Oxford. There is a lot of development going on in big companies or academia. Most of those are open source, so anybody can look at the model checker developed by University of Parma or at Berkeley or so on. Okay, so finally, to focus on our work, authentication is a process that prevents access by unauthorized user. So there are different ways of authentication. The most common is based on password. There is a multi-factor authentication where we can ask like 3 types of questions: what you have, what you know, and what you possess. Certificate-based authentication, without specified certificate, you cannot get through. Token-based authentication generated by identity provider. Biometric authentication, risk-based authentication. So there are different techniques, and we try to combine our image recognition, what we call technique, with risk-based authentication to allow access to certain part of the resources by a user without explicitly authenticate itself, but we should know with some degree of certainty that actually is not, that actually is a human trying to see that information, not web robot. So there are different types of pages that we allow to access for information about current interest rate or things like that. We can allow even non-registered user to get there, but we cannot allow web robot to get to that page and so on. So for this authentication technique that we are experimenting now with, we create some questions that are a little bit different than common questions. So in a set A, we put pictures of, for example, could be something like cat, mouse, and some animal mom feeds a baby. So what we are looking here is not what is on the picture, but what is also a relation between pictures. So in order to understand a relation, you first need to understand the picture and then to understand what is actually the relation between images or relation between objects inside one image. The answers are in a set B, where we have lion, alligator, and hamburger. And the user is there. That can be some person or can be robot. So if person understands that something in these relations, it's maybe related with the eating or feeding, it would be clear for him that actually the answer B is hamburger. So in this case, you put yourself into story, and a robot cannot put itself into story because for him there is no food on a set B. So I will talk a little bit more about this, how we put everything together. This is just kind of a mathematical description. If we have one set of 3 pictures, if we have relations E, only 2 elements in that set satisfy this relation, and then we have answer that is getting some relation with the subject, and out of 3 possible combination, subject lion, subject alligator, and subject hamburger, the only one that satisfies this relation is hamburger. So the goal is to create a question that is very easy for human, but difficult for machine. And we think this kind of approach, and this is already patented in Canada and USA, is a good approach, but at the same time, it's not enough, because just by guessing, robot can with 33% of chance be correct. So we need some additional layer that is actually risk-based authentication that collects so-called silent information like mouse movement, keyboard typing dynamics, operating system, user agent, etc. So that is actually the one that helps us to distinguish human behavior and behavior of the web bot or robot. So even with this, just one shot, one question may not be enough. So we may need to ask multiple questions to be positively sure that actually the subject is human. But we don't know how many questions. Is it enough 2 or we need more? And to answer this question, we need also to know what kind of damage will be created if robot gets through, and also how inconvenience is for a user if it needs to answer a lot of questions. So what we do as engineers or researchers, we try to put like a range and show the information to business people, and then they will decide what is acceptable risk, what is acceptable level of convenience for user, and so on. Based on that, they will actually decide if this system has a future, if this is usable or not, or cannot be commercialized. So all options are open, but what we as researchers and engineers are doing is trying to create some model that will generate quantitative evaluation of the system, and then we'll provide that data to them. So we are out of the question for this step of commercialization. We are just actually giving information that actually decide what is the scope of this solution. So to model our system, we have few assumptions. So we decided customers or subjects into 3 groups. So now we are modeling people, and based on the skill level, we divided them into group sigma 1, sigma 2, and sigma 3, and also we divide this story into 3 levels. Some are very short, very easy to answer, some maybe a little bit bigger, more difficult, and the most complex stories we call grande. So this probability P00, P01 is actually probability that particular customer level will be able to detect to have correct answer P00, and incorrect answer is P01. P02 and 03 are related with the risk-based authentication. This is probability that we can identify a subject as a human. So the first attempt to build a model is actually just kind of flat, not hierarchical probabilistic state chart, where we have initial state on event E0, that means select the correct answer. With some probability, the answer will be correct, with other probability will be incorrect. And then the risk-based authentication system, with some probability, will detect that user as a human or as a robot. But this is not enough, because there is high probability that even robot can estimate correct, and that the system will not be able to distinguish between human and bot. It is relatively small, much smaller than to detect human, but it can happen. So in order to improve this system, we add loop feedback, where actually multiple times we are going through process of selection of image. And we also added so-called rewards in each of those states. If we get through correct state, we get this C variable, one reward, and for incorrect, we also add one. When we end up on a human state, we add one to variable H and to both variable B. So this is actually very useful when model checker generates graphs. It can actually shows us the values of these variables, and we will know actually how the things will perform during each step. So in this example, we show maximum to 5. So maximum in 5 steps, we'll see how the things are going to change, evaluate. So here I have a snippet of the code, and we can very easily correlate what is on our diagram, transition E0, E1, E2. E0 is select image, E1 is bot detection, and E2 is to try again. So we have this variable root that is going through all states, and there is some condition. If that condition is satisfied, with some probability, we'll take one direction, with other probability, you are taking the other direction. So basically, that's all very intuitive, straightforward, and relatively simple model, but we believe very useful. You know, there is so-called old statement that all models are wrong, but some are useful. And we believe this model is useful because it gives us some information that we intuitively expected, but we didn't know exact number. For example, I have here 4 formulas, rewards formulas, that actually is looking what will be value of those variables that we specified for each state when system finally goes to the select image and counter each step. So steps are going from 1 to 5. That's why on this graph we have steps from 1 to 5, and expected value of all of these 4 variables are actually shown on the graph. For example, after 5 steps, we'll expect that actually 4 times we'll end up in a human state. And this is for the sigma 1 customer that we consider least skillful. Only 68% of time is able to detect correct image. Another information that we are generating for this least skillful client is that in particular number of steps, how many times it will select correct state. So for example, in the first step, as we know, it will be 68%. After that, in 2 steps, with less than 50%, we'll have 1 correct, but also we'll have possibility of being correct 2 times. So it's maximum to be 2 times in 2 steps and so on. On 5 steps, we have like 15% of probability that all 5 times we selected correct, and there are like the biggest probability is that we have only 2 times selected correct, and so on. So this information should be further analyzed to figure out actually if 3 steps are enough and for what kind of system, or maybe sometimes 2 steps may be okay, and so on. So this is for least skillful customer, and also we have for the same customer how many times end up in incorrect state in each step. So we had 68% of time to be correct. So on first step will be just 42%, and then the number will be changed in after 5 tries. We will have possibility almost less than 35% that all 5 times it ends up in that at least one time ends up in an incorrect state, and all 5 times ends up in incorrect state, very low probability. So based on this, if we have like 4 or 5 steps, we can, with a high probability, estimate that actually it is human. But still, this is for least skillful customer. For other 2 customers, sigma 1 and sigma 2, we get this kind of picture. We can see actually that the slope is stiffer here, so we have better result for more skillful client, but still there is a possibility that actually the both will get through. So the question is what could be tolerated, and what we can do to decrease this probability. Anyway, so for us was the task to have this picture and to recommend what could be further work on this. So by the best of my knowledge, this is kind of first time we were using in a bank probabilistic model checkers for this kind of estimation, quantification. I cannot expose more than this, but I think this actually shows the direction of work that we are getting there. So far, we found it is kind of exciting and very interesting to have probabilistic model checker as a part of the software development system. Earlier, we deploy our model better for us because we can identify some weak points, or we can see, okay, this looks good. We can implement and test in real environment. The values estimated by the model expected false negative rate is in the range 3.125 to times to 10 minus 5 to 2.43 times 10 minus 10. This is the worst possible situation for a less skillful client and the best possible situation for most skillful client. So the main limitation of this system is that it requires intermediate or advanced user or more advanced risk-based decision engine. So usually this 3.1, although it looks very low, cannot be accepted, because if we use this kind of authentication to allow access to accounts, this is still not acceptable. But to allow access to some of the information that are not available by general public, but may be of interest for potential users, we can tolerate this kind of false negative rate. The probabilistic model checker is useful tool for quantitative evaluation of authentication techniques. So this is our kind of statement after this experience, but there is now a lot of other things that are coming up. Can we use like a machine learning model to dynamically change probability based on previous success failure? Can we include so-called non-deterministic transitions? All now transitions are probabilistic. In non-deterministic, we don't know at all what with what probability will go which way, and that will go to less accurate estimation, but at least will cover all more possibility. So we plan to apply similar techniques to more complex probabilistic models in financial industry, and now I'm trying to build a bridge between bank and the university. I think would be a win-win situation for both sides, and to create a model that combines other authentication techniques like biometric authentication, that for sure we believe it will almost eliminate false negative identification. So basically, that's it. I was preparing for tomorrow, but thank you for the opportunity to give this presentation today.